All right, welcome everybody. It's the 14th of October, 2025, and this is Open Research Institute's Projects Meetup. And what we do is we talk about what we've done, what we have planned, if we need any resources, and if we have any roadblocks, anything that is in our way. So let's go ahead and start with Aaron. Aaron, you have the floor.
So, so I've been continuing to work on the DVBS2 encoder port using OpenCPI onto the ZC104. Last week, I was able to implement the RRC filter that goes right after the encoder. And so my block design, I'm gonna try to show some pictures, see if that works out. It's basically the encoder and using streaming AXI, for a compiler, and then this gets wrapped into an OpenCPI primitive that gets loaded into OpenCPI as a worker and into the overall bit stream that gets onto hardware. So I was able to do that. I'm on my phone, so bear with me. Trying this for the first time. I wonder if I have to stop and then share again. So I can write that to a file, like I said, and this is what it looks like. So the PL frame, enabling the PL dummy frame generator. And you can see that on the right is the time domain, and the left is the frequency domain. So you see that shape, the pulse shape from the RRC filter. And yep. And then in addition to this, I hooked it up to the analog devices 89361, and I was able to see similar output in RF. So what I need to do, and what I set out to do last week, but I got distracted with this, was start the other side of the implementation on the PS, was generating the BB frames such that we can fill in the rest of this data, because right now it's just the PL header that's shown here. And then everything else is set high for both the in-phase and quadrature data, which is not what we need. So I'll be working on that, implementing the transfer from the PS to the PL, and generating those BB frames on the PS and feeding the encoder with actual valid data. Yep. In addition to that, I finally went ahead and ordered all of the pieces to build my mini tuner receiver, because I have a Pico tuner, but in my experimentation, I wasn't able to get or replicate the GSC packets end to end using the Pico tuner, which is the latest version. So I'm building a mini tuner so that I can validate that we can get DVBS data, Ethernet data, using DVBS2 GSC through the system and across the link. So I get the parts from DigiKey tomorrow, and so I'm going to spend some time building that. Shouldn't take too long, and then when I have time, replicating some of the work that's already been done by you guys. That's all I have.
Well, that's quite a lot. Oh, thank you so much. I think October is going to be a big, a bunch of step forward for the work that you're doing. So thank you so much.
Mm-hmm.
Is there anything that you need or anything we can help with?
Nope, not at this time. Thank you, Michelle.
Okay. Yeah, keep it in mind if you run into a roadblock and it's annoying or difficult, then or if there's something in the code base, either file an issue or raise it on Slack, and we'll look at it. So yeah, thank you so much. This is going to be a very powerful bit of work going forward, and just super happy, really appreciative. Thank you. Okay, and I'd like to welcome Mike Parker. Hey, anything you want to share about what's been going on? Bring us up to date, what you got planned, and if there's anything that we can do to help you, or any roadblocks that you're having that you want to talk about. So the floor is yours.
Okay, well, I didn't really come in here to talk. I expected to hear what was up, catch up. But I've been spending most of my time working with the University of Arizona CATSAT program. That satellite's been on orbit a little longer than a year now, and we're expecting about 1 more year before it augers in, but due to friction of the atmosphere. And so I'm sort of a hanger-oner now with the students doing all the work, which I like that. And but we still have the data transfer DVBS2 coming down from the spacecraft. This is the low orbit spacecraft, so the Doppler shifts are horrendous. But that's been a very effective downlink data rate, much better than our UHF transmitter. And that's about all I have to say.
Yeah, I think that I recall the conversations where you were curious about how it would hold up to Doppler, and I remember walking through it, and I'm so happy to see it confirmed in orbit. It's always nice to see.
Might add one thing is that we have put signals through the thing, and it turns out this is a software radio, and one of the modes is just be a repeater. So 5 gigahertz up and 10 gigahertz down, and so we've actually are starting to run that mode now, and that'll be open to hams in a linear transponder mode, and that should be coming out on the website within the next week or two as to how to get at the satellite. And obviously with the narrower beam you end up having to program where is the satellite pointing, and if I point the satellite at Dallas and I'm in Tucson, the people over in California aren't going to hear anything, and vice versa. So there's going to have to be a little bit of experimentation there. But we think we solved the Doppler problems just like other hams and other frequencies have solved it by de-Dopplering.
That's right. No, it's very exciting. And so for people that are listening that may not be familiar with the CATSAT, where's the best place for people to go if they want to get caught up and to see if they have a station already that might be capable, or if they want to go ahead and start working on a station to use it? Where's the place for people to start?
It's embarrassing because I don't have the exact URL, but it's basically do a search for University of Arizona CATSAT, CATSAT, and you'll find things will come up.
Okay.
And,
yeah, what I'll do is I'll go find the exact URL, and I'll make sure that it's part of this recording. So I'll go ahead and make sure that people have the exact link to click on so that they can get, because this is a wonderful opportunity. And yeah, I'm looking forward to seeing what I can do and helping other people take advantage of it.
Wow, did I hear it correctly? That's 5 up and 10 down?
That's right.
Whoa. Not that many sats up there for hams that are that use those bands for comms.
That's right.
It'll be one of the first, so
yeah,
hang on to your frequencies.
You bet. Yeah, we're doing our best.
Hang on to the keep them alive.
Yeah, this particular frequency allocation or frequency plan is the one that we use for high Fourier and for opulent voice up, and then the DVBS2 down. So we're solidly in this camp and super happy that this got launched and is working. And thank you so much to Mike Parker at University of Arizona and all the students that have worked very hard on this.
Yeah, the students have been carrying the spear for the last year or so, and I haven't even operated the satellite, and they operate it.
Is the 5 gigahertz band going to be a problem with the new Wi-Fi allocations?
It's not going to be a problem for me. I haven't seen anything about them it's 5 point. I'm not going to tell you because I'll screw it up. But the exact frequency, but it's one that has been allocated to ham use, and it is in the IRAU satellite use, I think.
Yeah, we have a satellite uplink on 5 gigahertz and a really nice terrestrial allocation for experimentation. So that's one of the reasons why we picked it to focus on for 5 up, 10 down. So we're in good shape. There is always the concern about RFI and other, services coming in and using it. That's always a concern for us. But so far, 5 gig is a good choice and used pretty heavily by amateur radio. So, but we, of course, I mean, the advice here is to be vigilant and just stay involved. So stay involved with any organization that is active in regulatory work so that we can keep access to this band. Do all that you can to use it terrestrially and now space with this really nice uplink. And just thank you again to Mike and all of the folks that spearheaded this and have worked incredibly hard to make it happen, and all of the students that implemented it and maintain it and are operating it and getting a lot out of this. But a huge learning experience for all of them.
So just to answer the question about what it takes to get through the satellite, we aren't sure yet, but right now I'm building a station with 2 1-meter dishes, one for each frequency. So I'm repurposing a TV receive only for the 10 megahertz receiver, gigahertz receiver. And 10 watts of transmitter power is what 5 gigahertz uplink.
And we do have a dual band feed for 5 and 10.
I was going to ask you about that. I think you sent me one, but I don't think it was 5 and 10.
I think that we have the 5 and 10 dual band feed. This was a design that W1GHZ Paul Wade made for us back in, I think this was probably 2018 or maybe earlier. And the designs in the repository, we've made a couple of versions of this metal machined. I think Paul did that on his in his garage. And we also have made 3D printed metallized versions of the feed so that you can have a quick and dirty prototype to check with. But so we do have a dual band feed for 5 and 10. And so if anybody wants to help with that.
If you guys have another production run on that, let me know. I'd like to be interested in snapping one.
Yeah, because 1 dish, easier to point than 2. That's why we did it. But you probably will have the 10-24. So there's also a 10 and 20, 10 up, 24 down, or dual band feed for 10 and 24 that we have. If anybody wants one, we have a box of those. But yeah, the 5 and 10 design, we can get one to you. That makes it a little easier to use this band. That's one of the first things that we did. So okay. I'll talk to you offline and make sure that so if you have somebody that can 3D print it and metalize it, then it works. We tested it and it actually will work. You do have to have somebody with a little bit of arts and crafts skill to apply the metallic, essentially metallic paint. MG Industries has a really good low conductivity paint that either you can paint it on by brush or you can spray paint it. Those are the sorts of things that you can do with a 3D printer. If you have somebody that has some machining experience and has a machining setup capable of making the feed, then that's an option too. And we can talk about maybe a run to get more of these designs out there. So yeah, let's talk more. I think that would probably help. Since there's about a year left expected on the satellite, we would like to help you get full use out of it and to make it easy for amateurs to use and experiment with it. And it sounds like it would be really ideal if there's any way to run things, it sounds like linear transponder, then we can test a lot of what we've developed in terms of waveforms through it at LEO, which is, we expect it to work. And it'd be really wonderful to see it.
I'm sure the students would love to talk to you about that.
Okay, yeah, please let them know they can reach out anytime, and we are here to help. That's why we exist. So yeah, please pass along any information on how to get in touch with me or anybody else, the organization, and they're very welcome. We're here as a resource and to help get designs and student work and amateur work in space and working terrestrially as well.
So are those feeds septums, or are they just linear polarization
Oh, these are so it's linear, but it's
on the
cross.
feeds?
The
Yeah.
feeds are cross. So they're when you look at this is going to look like something that you would find in a dish, corrugated, stepped on the outside. But the back in the back of it that connects to
Right.
the waveguide, then what we've done is linear up, and then at 90 degrees out is the linear down. So they're cross polarized both ways.
Oh, okay.
That's
They're not the
style.
septum ones that have the automatic cross polarization.
No, but that is an option. We do have a volunteer that has made a few of the septum style. Yeah, we've just had really good results with the cross polarized linear up, linear down, 90 degrees out. So it kind of depends on what the satellite's doing. So we have a couple of options, but I believe that the CATSAT is linear up and linear down, and they're cross polarized, and that's how you get the separation.
Is it stabilized, or is it just tumbling?
It's stabilized, but it
Oh,
is.
great.
Both 5 gigs and 10 gigs are circularly polarized.
Oh, okay.
Oh,
Yeah,
okay.
there's going to be some loss.
That makes sense.
Just a
Yeah.
patch.
Okay, good to know.
That makes sense. Yeah.
Probably can still help, but we can run through the numbers on any loss and
Yeah.
figure out anything else.
I'm using linear to talk to the satellite just because I am.
Yeah, should work. We'll double check and move forward.
So those 1 meter antennas on ASIC mounts to track.
Yeah, and that's I'll report back maybe to you some other time in the future as to whether that worked. But the beam width is about 1.5 degrees at X band, and I think the thing's wiggling about 2 degrees back and forth as you.
Yeah, that sounds about right. I'm confident, but as y'all know, I'm an optimist. But I think it will work, and all of this is going to unfold over the next week. It sounds like.
Yeah, they're ready to do it as soon as we have a station that wants to talk to us.
Right. Okay. Well, we'll do all that we can to get the word out.
I have one from at home that I'm building, but I'm not quite ready yet.
Right. Yeah.
But they're ready.
Very good. This is fantastic news. Thank you so much for telling us about it, explaining it, and we will do all that we can to spread the word and to get more stations interested. This is a really, really great project. Very, very happy to hear all about it. Anything else that we should know about?
Well, probably, but you didn't hear it from me.
Just out of curiosity, who put it up? Who put up the CATSAT? Was it SpaceX?
It was the Firefly.
Oh, Firefly. Okay.
And it was somehow the university had a deal with NASA that they wrote a proposal, and that's where some of the money came from.
Great. Yeah.
Cool. Yeah, thank you so much. This is good news, and a lot of work. So we will, like I said, we'll spread the word and try to help out with any sort of dual band feeds we can come up with to let you know about the design that we have and maybe take a good hard look at anything else we can contribute. Awesome. Okay. So Matthew, plenty to talk about. You have the floor.
All right, thank you. Yeah, we made some progress. I've been having a issue documented for several months for the differential encoder-decoder operation, and finally got that figured out this last week, and so that's committed to Maine. and worked in the simulation, and we've got some good results in the lab with that as well. So that was the main thing I'd been looking at. And then I'm just doing some more code cleanup here and there, adding the synchronization resyncs for the clock domain processing for the control signals. So that's coming along, nearly done. So I think that's the updates I have for the moment.
Yeah. So yeah, the sorts of steps forward that you've enabled with some key work here is to resolve a kind of a long-standing differential encoder-decoder hangup that was not exactly getting the data across from in to out on the modem the way that we wanted, and that looks like it's been resolved.
I think so. Yeah, I mean the issue started when we first started to try to add the sync word so that we can when we were trying to transmit a sync word, and so based on the Massey sequencer or encoder, we expected a certain output, but when we put in the sync input that should have given the output that we were expecting, it wasn't happening. So that was the key or the clue that the encoder wasn't correct. After I had fixed the encoder, then the receiver wasn't working any longer. And so that was just strange. So what I was doing, the way that I went about correcting this or figuring the issue out finally is I thought it would be useful to have a encoder to decoder loopback that doesn't go through the modulator. And in doing that, I had to work through some of the issues in the encoder and decoder, and ended up, I thought I had integrated the Hodgkin-Schoons encoder previously. There was a commit for it, but it wasn't what was there. So I updated to that encoder again, and there were no changes actually required to the decoder, and everything just worked. Oddly enough, I need to go back to the encoder-decoder loopback. It's not quite working right, but it was that process was kind of key to finally seeing all the issues and getting them straightened out. So at least in simulation, everything looks good, and I think we're seeing the results we're expecting in the lab as well, if I understood correctly on the Slack.
Yes. Yeah, that this kind of goes to show that the sorts of testing that we're talking about, and also that the loop back for the differential encoder is different than the digital loop back inside the FPGA, which is a different loop back from going all the way out to the antenna port and then looping back either over the air or over a conducted cabled link. And with all of these different levels of loop back, we've been able to isolate problems and solve them in a systematic way. So the steps over the past week or so have been big. Before we knew that the internal, we have an internal a pattern generator, a pseudo-random binary sequence code. So there's actual hardware in our modem design that Matthew made that generates what looks like random data in a systematic way. And so that was actually working over the air. So when we put in data of our own choosing, arbitrary data over the AXI stream, and it did not work at all, this was kind of confusing because, well, it works over the air with PRBS, but it doesn't work over the air with AXI stream. And so these different levels of access, being able to loop back into the modem, to be able to test in the remote lab versus test in simulation, which are two different situations that involve different parts of the hardware. So this sort of dialectic approach to it is resolved things. I'm sure we wish it would resolve faster. We always want things to turn out and resolve quicker, but the pace has been really very good. So we're moving through some significant issues and gaining a lot of traction in terms of the modem capability. So at this point, we now have PRBS working. We have arbitrary data that you would send to the modem from, say, interlocutor or equivalent, and it's working. We also see that it's synchronizing or, being able to figure out the actual frequencies and phase relationships and lock on to the signals that it's getting pretty quick. So what Paul has proposed is to really do a study and see exactly how much preamble we need. Because right now in our spec for Opulent Voice, we say that we give a full frame of preamble. We may not need nearly this much. As a comparison, like over in LTE or 5G, you see that the preamble and training sequences are much shorter than a frame. We may be able to get away with this, or we may want to really look hard at like how long the preamble can be to dig the signal out of, a very poor SNR environment, which we may see. Or, do we need a long preamble to deal with Doppler, things like that. So this is going to be a really neat next exploration that has been enabled by Matthew's very hard and very competent work. So thank you so much, Matthew, for making such a really amazing modem and chipping away at this problem with the encoder. For something that on paper looks very simple, it actually isn't. And the things that we've dealt with have been very tricky. So it's very exciting to see it work.
Yeah, it is. And, I think, that this is, as far as the education approach here, the encoder is very integral to the modem in this design. MSK doesn't seem like it should be so integral in general, but certainly the Massey and the Hotchkiss-Schoon's papers, the encoder-decoder is integral to the modem design and operation. So, that's where we're at the moment. It is, but we've designed this in such a way that we should be able to experiment with other designs and design approaches and still keep the MSK. So it's neat in that way. I'm also hoping that, I don't know if we've seen the split spectrum issue in recent times, but
No, we haven't.
Okay, well, if we haven't,
Well,
if the encoder bug that we had might have been part of the split spectrum issue that we've seen at one time.
Sounded like Paul, go ahead. Did you see?
I can't remember the exact circumstances, but there was some weird experiment I was doing where I did manage to get it to come up with split spectrum, but I haven't seen it in routine testing in a while.
Yeah, we'll keep an eye out because that was very interesting.
Yeah.
And it could be some sort of hallmark of the target that we have. That could be a Pluto thing.
Yeah.
Because there's a lot going on there too.
Yeah. Right.
So, but it was
but
very,
that was very
very
odd. I mean, we wouldn't have expected it. So I was wondering if it could,
No.
we know we had an encoder bug and it was there, present when we were seeing that split spectrum. So, maybe it's related.
Yeah.
And then the other thing is, yeah, I think, the modem locks fine without a preamble or sync word, which I would expect it to. I think, in general, the sync can help, it might reduce the acquisition time a little bit. I wouldn't expect a lot of improvement, but yeah, if we're in low SNR or Doppler, that might be more helpful. So, yeah, we do, I think, starting to experiment with impairments to
Right.
see, optimize, if we need a preamble, how long it is, that sort of thing. So yeah, that makes good sense.
Yeah, I think a good characterization of like exactly how much preamble you need all the way down to totally unrecoverable would be that's what Paul's interested in doing. So we'll do that. Right now, we'll just
They
keep
do some waterfall
no,
curves for the design as it is, and
right.
then add some impairments and see where we are too. And then the other thing I think that should probably go on the short-term development list, other than cleanup, is a proper lock circuit, so that we know that, so then the modem will tell us that it's locked and working. I have some papers that I think are relevant there. There are simple things we can do. Just counting the amount, like min-max excursions of the loop gain or the loop
Right.
accumulator, right?
Right.
So that's a simple way to do it. So once the accumulator is staying within some small range, then we can say, yes, it's locked. But I think there's some other more, maybe more useful, what should I say? Fine-grained lock circuits that we could look at as well.
Right. And then I know we've talked about this before, but just having, when we talk about locking and synchronization, this relates very heavily to the costless loops and the PI gains, and having like if you are not, if you're an idle, then your gains are these. And then once you acquire the signal, then you can shift to another set of gains to really kind of pull it in. So we're open to and looking at that as well, as part of the implementation that we will offer. So that's that's out there, that exists as a thing. So we're aware of that, and also looking for the chance to kind of test those and maybe have some numbers for the use cases that we're talking about. So I think it might help, but like the performance that we have seen just in the lab, that it locks pretty quick. Just now this is on a bench with no Doppler, fairly strong signal, but that's very heartening, and it just shows that things are working, and that some of the concerns that we see in simulation, because I got to tell you, yet another lessons learned. It might not work in sim, and it might work in hardware. It might
just unusual.
and vice versa. This is just a thing with FPGA and ASIC design that we from our educational mission. This is a real good case study of things sometimes don't work in sim, they work in hardware. They were not really a problem. You can spend a lot of time trying to fix something in sim that is not a problem in hardware, and vice versa. You might be so confident your simulation works and the hardware absolutely falls down, and you can find the problems, and good communication and going back and forth from one world to the other. That's what you need in order to get designs delivered. So that's our goal here. And, not just to deliver a working design, but to explain these sort of process things. This is not something you really find in school, but explaining it pretty clearly and making it relatable, I think is right up our alley. It's there's some good examples here. The next big parts of the design are the making what should come out next. So we cleaned up and made the 32-bit access thing happen. That resolved the extra zeros that we were seeing. Some of the next things that we're talking about doing, or the next thing that actually has code that's almost working, is getting AxiStream standard signals across the board. And also doing a FIFO for the transmit. So transmitting into the HDL to have it already set up as a frame of data. So to go from just streaming stuff through and testing, which is what we've been doing so far, to going to a frame aware HDL. And then after that, seeing if we can fit in the randomization, the forward error correction, and the interleaving into the HDL. Already know from a couple of experiments that if we can't move all of these new buffers, because it's arrays and buffers that are required in order to do this, and we can combine things like randomization can actually be combined with a forward error correction. You can do both of those on the same thing as you go along, but you have to do the entire thing before you then interleave. So that's at least two pretty significant sized buffers. If we can't move those to BRAM in the Zinc, we're over the size for the 7010. So that's going to be a big challenge. We're finally running out of space on the 7010. And if we do, not a disaster, we do have other options. It just would be really wonderful if we can keep this on the Pluto. If we have to do this stuff in software and just send over a completed buffer of ready to transmit, well, that's what we have right now. So it's win-win. But we will need to figure out
modular, right? So we could have, like, if you could still have all that stuff in hardware for certain systems, right? Like
yeah. Yes. Yeah, that's true.
I mean, it's not
last time we talked about this was.
Right?
Oh, sorry. Go ahead. I didn't mean to.
No, I was just saying I don't think it's all or nothing. For the standard Pluto, yeah, you may not be able to do that stuff in hardware necessarily, but in some of these other, ones with have the 7020, the Pluto clones have the 7020. You could, right? So you could have, a design that targets the Pluto and the design that targets the 7020.
Yes. Yeah. For example, if the target is the 7010, gosh, you might need the whole thing done for you in software, and what the 7010 or what the Pluto would do is only add the sync word and push it out, which is fine. That's a lot of work that it's doing. And then this would be like a register configuration. You would write to a register like, okay, or let it figure it out, and it would self-configure. If the target's 7010, more has to be done in software. If it's a 7020, we actually might be able to activate all of these functions in hardware, which is kind of what we prefer. The end result is lots of different systems that work, different FPGAs that work, and beyond that is to bring this to an ASIC, to be able to offer to the community an open source ASIC design that does all of the functions. So that's kind of where we're going long term with this, and making it modular to stay loyal and honest with the modem module approach that Matthew has spearheaded. This would be right up that alley. You're right. So thank you very much for the correction. It's not all or nothing. There's a variety of functions that can be brought in depending on the size of the FPGA available. This is definitely a computer science problem. Load balancing between your general purpose processor and your FPGA is like a core problem in software defined radio.
Or any embedded.
This is
the hardware software partitioning is a significant part of system design for any embedded system.
Very true.
So this is another aspect of where OpenCPI can really shine, because we have the concept of what's a work-alike. So you have these core units of function like the scrambler and the descrambler and things like that, and you implement it. Do an implementation in HDL, and you do an implementation for the general purpose processor, and then at runtime you can select which one of those you want depending on how many available resources you have. So this is an exact problem where in our case where the 7010 doesn't have enough, so you move some of that to the processing side. But it's still essentially the same application, but the elements are in different processing elements based on what's available. So as soon as I can get the DVBS2 encoder as an example and how it can be ported to different platforms, it'd be another good chance to show off what it's capable of. And now when I hear, it sounds like the encoder and decoder are in a better place, because when I was experimenting with it, I was running into issues because I wasn't using the pre-canned PRBS generator. I was using one that was already generated for OpenCPI, and we weren't getting the data that I was expecting, which is something that you guys have recently solved too. So I can get back to it and give it a shot again now that these bugs were fixed.
Yes, and they're in main. So the main checkout will have working, differential encoder, decoder, and also will be all tuned for 32-bit AXI transfers. So those are there today in main. There's some other branches that will do some more work, but there should be no difference in the differential encoder, decoder, and the correct AXI width moving forward. So you should see what goes in should come out now, which is awesome.
Okay.
Yeah,
that's awesome.
What you want.
Yeah.
I might make a suggestion that dating me. Back in the 70s, there was a company called Microdyne that built really great hardware receivers, which I had one in my lab for many years. And what they did to monitor their phase lock loop is they simply brought it out to a speaker, and if they were locked, there was nothing coming out except a little hiss. And if they weren't in lock, there would be a beat note between what the right frequency would be and the frequency of the receiver's oscillator, and you hear that as a tone. So as an operator, what you would do is you had another switch that opened and closed your loop, and you'd open the loop, you'd tune the receiver, listening for that beat note. As soon as you heard it, you'd let go of the switch, and it would lock up. And I've often thought that it would be nice to have such a feature on these digital circuits to do a similar thing, but nobody seems to have done it.
The trouble being with reasonable bandwidth digital circuits, the beat note usually super audible, so you can't really hear the shape of the waveform when it's 80 kilohertz wide.
Maybe there's a way to
You go
translate it
into
though.
you go into it and you grab the error. There's a feedback wire that carries the error signal back to an integrator, and
Yeah, but you're faking it then, really.
that comes out at a slow frequency.
That's really cool. This reminds me of some techniques in embedded firmware where when you're trying to figure out why there's a difference between the robotic arm like missing the stuff in the factory versus your code which looks totally right, that you just convert the error to an audio signal and just listen to it. And this is a technique that I remember pretty clearly early in my career. So you've reminded me of something that was actually very useful. You're using the human hardware to catch the issue.
Who needs an FFT?
Yeah, that's a really cool idea. No, thank you, Mike. That's definitely some food for thought, and reminds me of things that I actually used in the chicken processing factory that I briefly worked in because that was the only option really on site was to make a audio signal come out, and if it whined weird, then you knew where the problem was. So, yeah, thanks. Oh no, it's maybe
You notice in which frequencies?
I think he's talking about like the Costas loop locks and whether or not you're in lock or not, and those signals. So right now, at least, I have to like look at a very complicated screen to kind of and dig down and see what's going on, or Paul's representation graphically with the graphs that he makes. So getting an immediate feedback that you can hear as a person is a good tip.
Yeah, okay. Yeah, it should be close to a pure sine wave. If it was like, no, I guess it's going to be it shouldn't be any frequency, right? I guess well, you're going to if you take that kind of voltage, and put it into made it sine, drove a sine wave from that speaker, then yeah, I guess it should be a constant frequency if locked or not locked.
If you're locked, the phase error stays to be near zero. If you've lost lock, then it's whatever frequency your oscillator is difference with that frequency. So this would be UHF in those days, and it would be signals a few hundred kilohertz wide.
Mm-hmm. No, that's a kind of a neat way to do it. I mean, we have that to a degree in terms of if you look at the simulations, you can plot the phase error as an analog signal in simulation. You can clearly see it's oscillating around and then flattens out. But it's hard to capture that data in, say, a memory and then read it out, because the memories don't have, infinite depth. But if you took that out to a DAC and hooked up to a speaker, that would be tell you right away if you were locked. Kind of neat.
Yeah, that'd be fun. Yeah, I thank you so much, Mike. That's really cool. All right. Let's see.
Well, I was going to say the other thing that's kind of I would say still a pretty big open item in that, and it affects what Paul was suggesting in terms of the testing we want to do with the preamble, and that is figuring out what the loop gains are supposed to be. We found loop gains, I think, that work.
Yeah.
But we've not, I think, analytically been able to arrive at a set of loop gains that make sense. And certainly like what's working in the FPGA or in the simulation rather, doesn't necessarily work in the lab and vice versa.
Right.
We're saying, so I mean, I think we're just really, we need to, so I mean, I think that's an open item.
Yeah.
We don't have an analytical way to set the loop gains. And so right now it's just empirical, and I think we're far from optimized.
That is a very good point. So what we have right now is a set of gains that seem to work in the hardware. And I think that Matthew settled on these with lots of testing and probing. And then we have a set of gains from an analysis that we got from Gardner, a combination of a huge amount of like lots of online searching through tutorials. Analog Devices had a really good like how do you set your PI, proportional integral controller gains. Um, and so then lots of academic papers from IEEE. Thank you, IEEE. And
And
so
Claudio,
we have a paper like that we ground through and it's all in MATLAB. And this was intended to kind of be a paper that we would submit to QEX. And the goal here, speaking as an optimist, was, hey, look, we calculated the gains using standard methods. We plopped them into the FPGA, and bang, it worked. No, bang, it blew up. So it just those gains are garbage. So we wrote several sets of PI gain search programs, some in on the processor side, and now some in test benches. So the PI gain search test bench that we currently have, it goes through and does a lot of testing, and you can see all sorts of amazing things happen, and they don't perform nearly as well as when you just go to hardware and you put in the PI gains that we have. When you take those PI gains that work in hardware, pretty rapidly converge the signal, everything's fine, and you put them in the simulation, it doesn't work. So what I did is I did like a two-dimensional search because you have a P and an I. This gives you a grid, and then I see patterns. Okay, that systematic pattern needs to be explored, and that's pretty much where we are today. So work will continue, and we will figure out what the heck is going on. But you know what? I'm totally satisfied with the gains that we have right now because they perform really well in the testing in the lab, and we'll just keep at it. So it's a both and kind of a parallel effort. No, the paper's not yet ready to submit to QEX or wherever, but we will eventually get there, and we'll have a really nice explanation of, here's your simulation, here's your math, here's your hardware, which are all three different things, so mathland, simland with your code and your choices versus the ideal case, that all the textbooks tell us, and then hardware, which drags in a whole bunch of other baggage. So these are sort of three different points of view, and one set of PI gains may not rule all of them. So this will be a really cool paper when we're done.
Yeah. Well, and this what you alluded to earlier. I mean, if we don't have somewhat optimized PA gains, or at least know where the real place we need to be is, that we're not in some local minimum, right?
Right.
Because if we don't have good PI gain, then we're not going to have good performance in low SNR environments and Doppler, right? So it's important that we at some point find that overall minimum so that we can, and we can once we know that, we can open them up for acquisition and then tighten them up for tracking. But so I mean, I guess that's all I'm suggesting. If we do a bunch of work with the preambles and trying to optimize the preamble, if we're not doing it with good gains, then it's not necessarily, I mean, it's right for those sets of gains, but it's not necessarily the best that we can achieve.
True. And it may not even be a linear relationship either. So the work that we do that Paul's talking about to kind of like characterize like how quick it resolves or converges for a particular preamble for a particular set of gains, may or may not translate linearly into the space. So we got a ton of really cool things to talk about and make understandable, to people that are interested in this sort of thing. So yeah, point well taken. Fortunately, we have really good code, I think now. At this point, we have good code for PI gain searches in SIM. So we take our source code and VHDL and simulate. And we also have good code for PI gain searches on the processor side, which for the hardware. So we can run searches which take a while. This is a lot of space to cover, and then we can compare both. So we have the tools for moving forward with this, and I think we're now rapidly approaching a point where the modem is stable enough and is, goes intas and the goes outas agree that we'll be able to march through this and tear this problem up. I expect we're going to see some very interesting patterns, and they're not the same. So the overall landscape in sim land does not match what we are seeing in hardware. So there's other things at work here. So I'm really looking forward to making it explainable and a good educational resource for anyone biting into this. Most of the time when you are in school and you're talking about proportional integral differential controllers, PID controllers or P controllers or PI controllers, PI is what we're using here, you just really get the math, and that's pretty much it. And when you bring it out to actual implementation with all of the things, all of the different factors, that's something that you really have to learn the hard way in a silo, usually at a company, and they don't really like to talk about the failures or anything like that. Or they'll just tell you, this is what you do. Look, we earned this knowledge, use these and move on. And then anything, a variance from that is not ideal. Like for good reason, because you can see how tricky it is. So this might be something that we can really kind of contribute a good educational module on this exact sort of work, not really covered in depth in the DSP world. So looking forward to that. It'll be hard earned. And thank you very much, Matthew, for the leadership here. It's very appreciated, and all the code. And over the next week, we should be able to answer a lot more questions and have more of these functions in there, or at least defined. Like we do have a pretty good framer and deframer in VHDL. Looks like it's working. Doesn't quite fit in the 7010. So that's where we're at on that. And we'll have a lot more to report in a week.
Yeah, just one quick comment. I mean, if we can't get the Vivado to infer the memories, I've not been shy about just instantiating things from the Vivado library. So I mean, I've instantiated block RAMs when I can't get it to do what I need. I've instantiated the DSP slices that in my day job. So sometimes you can't get it to do what you need, or it's not optimizing right, and you just have to go down and do the low level work. It's not terribly bad. So I mean, if we need some help instantiating block RAMs, I'm happy to.
Okay. Yeah, my experience here is somewhat limited, and I know that you've got a lot more experience here. What I tried to do was just like I have an array, so an array in VHDL, and that's the buffer, and then tried to assign a block attribute to it, which usually works. But the way that we're trying to use the block the buffers in multiple ways with a somewhat sophisticated access method for the randomization, FEC, all that. And it just said no.
Yeah.
And taunted me with a error message that I did not appreciate. So that was what happened. I'm like, wow, that's not failed for me before. But it sounds like there's more that we can do here. And then over the next week, once we kind of get our fingers around getting the AXI stream stuff totally, standard, which is that's going to happen really soon. And then we'll be able to move into this particular question of trying to add as much as possible to hardware, and then assign it all to block RAM so it fits. It's really close though. It's going to be a tight fit with all of this in there. So, and like we talked about already, we can escape with modular design and doing more in software, which is yet another really cool computer science problem. So thank you. And anything else that we missed?
No, I think that covered it from my perspective.
Cool. Okay, so we have a quick take on Pacificon. So Pacificon is a ham radio event in San Ramon, California. And it's the Pacific Division of the ARRL. So lots of ARRL people there, all talking about the Homeowners Association rule that they're trying very, very hard to get through all the way through Congress. It had some success so far. I think it's passed the House. And this makes it easier for people that are in homeowners associations to have antennas. So, lots of hard work there. That was what the main thing that ARL really wanted to emphasize at the conference. I was invited to be the speaker for the Mount Diablo Radio Club or Radio Association. And this club is the one that puts on Pacificon. And so their meeting that is at Pacificon. They're the ones that organize the event, and I was like, wow, that's an honor, and it was an absolutely wonderful experience. So I talked about artificial intelligence and machine learning in amateur radio, and talked about what AI/ML is, history, context, and then some numerous sort of case studies and how AI/ML affects amateur radio. And it was a total joy to present. MDARC and Pacificon folks were exceedingly wonderful to work with. And the talk went super well. And we met lots of new people. There was, I think, 3 or 4 of us that were at Pacificon. And we didn't have a booth or a table or anything like that. But we went around and talked to lots of different people, went to lots of the talks. I tried very hard to attend everything that DVM had, since digital voice is their thing. And well, I think we're in really, really good shape with Opulent Voice. We offer a significant different product than anything that the DVM people are doing. And we talk with them and touch base with them a lot. One of the reasons that I wanted to attend Pacificon and pay careful attention to DVM is because they've announced some new hardware. And it involves a radio chip that has a pretty big bandwidth, a 500 kilohertz transmit and receive bandwidth. And this immediately made me think that, wow, maybe we could get Opulent Voice included in DVM at 70 centimeters and up. So 70 centimeters, that's one of the core frequencies for DVM. Unfortunately, it's very clear from their presentations that they're totally committed to the 25 kilohertz and down modes, traditional digital voice modes from the 90s through today. And so I raised it as a question, and I didn't understand the answer, I have to say. So I said, gosh, the chip that you've chosen, 500 kilohertz, what's up with this 25 kilohertz limit? Can't you, you've got a fast processor now and the new hardware that you've announced, so why not open it up to at least 100 kilohertz? And it was the answer was no. So they're not, that's not an option moving forward. So unfortunate, but okay. Learned a lot, listened very carefully to their 2 presentations. And I think we should just keep doing what we're doing. And we offer a pretty big upgrade to all of the digital modes out there in amateur radio. So we'll just keep at it and look for opportunities to be included in traditional or legacy ham radio products like that, and just keep making our own. So I think the path forward is pretty clear. And yeah, thanks again to Pacificon, everybody that was there that we talked to, and the new volunteers that we got from the event are so totally happy to meet up in person. Several people I got to meet in person. We all got to meet in person for the first time. Also, Ribbit. So one of the developers for Ribbit was there and got to touch base with him. And lots of interesting things are happening for Ribbit as well. This may be an event that we might want to have a booth or a table in the future to do demonstrations. That does seem to be possible. And, they have a fairly extensive vendor area, and they support nonprofits and clubs. They had a really nice swap meet. We scored there too. So if you're anywhere close to San Ramon, California, middle part of California, then yeah, check out Pacificon, and maybe we'll be there next year. And yeah, looking forward to seeing how all of the things kind of pan out from our activity over the past weekend. And we also were able to present at AMSAT UK Symposium. what we did is we had a recorded presentation because of the time zone challenges and because most of us were at Pacificon. And that presentation was very well received. What we did is we talked specifically about ORI, talked about what we do, our mission, history, and then talked about our projects that have to do with space. So our regulatory work, remote labs, and the equipment choices. We talked about Hyperia and the space segment and the design decisions there. And we talked about opulent voice, uplink protocol and the progress there. And yeah, that was a wonderful opportunity. Thank you so much to AMSAT UK for allowing us to talk about our work and to invite people to participate. And we look forward to several potential projects with AMSAT UK looking forward. I hope to be able to make some announcements very soon. And that concludes our agenda. The floor is open for any comments or questions, additional sharing. So please speak up with whatever you got.
I've got a few items. Further to Pacificon, we did score item in the swap meet, which may end up being useful in the remote lab. It's an enormous power strip. This is the kind of things you get excited about when you're trying to build equipment into a compact test bench or rack. Don't have a rack, although it's intended to be a rack-mounted power strip. The guy at the swap meet told me it was a switched power strip. I think that was a fib. It's a metered power strip, not even metered by outlet. It just manages to measure the power consumed in total. I think it's got an Ethernet port on it and a serial port. The Ethernet port is for management, and the serial port is for setup. And I'm building a cable based on an RS-232 serial connection, so I can actually talk to that and get it on my LAN and see what it can really do. But I think it's just going to be monitoring. But 16 outlets is kind of a nice number to have.
Yeah, it's built like a tank.
It is heavy. I'm predicting if I open it up to look inside, I'm going to find weights because there's no reason it could possibly be that heavy on its own. Anyhow, a little side quest for the remote lab. What I'd like to see next on Opulent Voice is I'd like to see the frame sync receiver get into the HDL so that the modulator demodulator modem in the HDL can actually give me frames. Because without that, we don't even have byte boundaries. Because the byte stream in Opulent Voice is not self-synchronizing without those frame syncs. So there's no way to know where the bytes are even. But if I get a frame sync and then line up my DMA of data on that boundary created by the frame sync, then I've got a nice block that I can work with as a frame, process that through Dialogus and up through Interlocutor. And once we add the appropriate receive functions to Dialogus, interface it with the ones that are already in Interlocutor, then we should be able to do actual over-the-air demos with real frame sync. And as we get the other steps of the modem, the scramble and the interleave and the FEC implemented, whether they're in software or hardware, I'll be able to do demos that actually use the feature set. So right now we're kind of in this awkward place where we can do fancy feature set demos in a fake way, and we've got data that's sort of flowing through, but without byte sync. But that one little key item, the frame sync, at least the receiver, but it'd be nice to put the generator in there too. That should be small and easy. Should be said by someone who is not going to be coding in an HDL, because you wouldn't want my HDL code in your product. That would get us step forward in a lot of different ways. So we could start doing some more integration and making it more real.
Yeah, I think that's since that's the outermost thing, really. When you look at our protocol, if a lot of times we are centered on like starting from the data and our, Opus codec, and then layering up the headers and then putting our custom header on it and then doing randomization and forward error correction, interleaving. We've talked a lot about that. But once you have all of that, that's still a baseband frame essentially. And then the real things, the markers that you're talking about are the synchronization frames. So these are sync words. These are actual real Barker codes. and they are very cool mathematical lighthouses. So they give you a bright pop, like here is the frame edge, here is the frame edge. And those things are super useful. And that's actually the last thing that goes on and the first thing that's taken off. So yes, that code in VHDL has been written already. It works as in simulation as part of the framer deframer. And that's a completely independent thing that should not break the bank in terms of the 7010.
Yeah.
So yeah, we'll do that first. In the neat thing about the live IIO sort of process that we're using, if you use analog devices like 9361, when you put your data into the TX buffer, whether it's just the 134 bytes of initial payload or the whole prepared thing that actually goes over the air that goes to the modulator that includes randomization, forward error correction, interleaving, and all that. Regardless of how much you put in there, when you ship it out, it creates a signal through AXI that says, hey, you've got a whole frame. And that's the signal that we're using in order to put things like sync pulse on, or sync word on. So if we get the whole thing prepared in software and all we can manage to do in hardware is to listen for that signal that, hey, this is a full frame, got it. Put on the sync word, ship it out to the modem. So I think that sounds like the next step, and that code's written, I'm going to say tested in sim, and we'll see how it works. And it should, when it goes out the door and then comes back around in the loop back, that's what we're constantly looking for. So every symbol that shifts in goes through essentially a shift register, and that shift register is assigned. Like I'm looking for the sync word. As soon as it sees the sync word, then the rest of that frame, and it counts, the rest of the frame goes through the receiver, goes and eventually goes through the receiver buffer off to the processor side so that it can go off to interlocutor. So that's working and hasn't been proven to work over the air. So I usually don't say it works until it works over the air, but it works in sim, and that stuff's been written, and I'm fairly confident that it's good, solid industry standard way of doing it. So we can deliver this to you soon. So
Yeah,
yes.
that'll be good. And I see Matthew's dropped off, but I wanted to thank him for pointing out that we need to do the loop gains thing before we do the preamble optimization. We might have gone down the wrong road, optimizing the wrong thing first, because I was ready to go ahead and start optimizing the preamble as soon as we had the frame sync locked in. But that's good. And I also want to remind Matthew, but I'll just have to remind the recording here and you guys who are still here along, is that we still have this nagging problem where sometimes you have to reboot the Pluto, and we do not know why or even how that's possible. So there's something going on with the fabric probably that is getting reset on a reboot that doesn't get reset when we restart the software. And we going to have to track that down and either put the reset code into the software, probably stealing it from the kernel, because if that's must be what's happening. It's the only thing I can imagine so far is that the kernel driver is resetting the hardware in a way that we don't know to do. Anyway, because that causes significant user problems. If that happens with any frequency, and it seems like it's pretty easy to trigger it by a weird test case, then that's an undesirable user experience. And those weird test cases will create themselves when we go really over the air with an antenna and a weak signal. Right now, not only are we not using an antenna, we don't have any interference, and we have no fading, no degradations at all. But we also have the clocks locked together on both sides, which is sort of a leftover from our debugging of the modem. I can undo that and see if things go to hell in a handbasket right away, or if they just get a little worse.
Yeah.
We tried that a couple of times, and that's what happens is you unlock the clocks and things get a little worse. And things that used to be zero error rate become small error rate.
Right.
But we haven't done the full matrix test of low signal strength and unlocked clocks and some interference and some fading. And that's not easy, but we can at least poke around in the corners of that box and see what demons are lurking.
Yeah, no, good points. Yeah, let's keep that on the mid burner.
Yeah. And I've got some things I want to do just to make testing at the interlocutor and dialogus level more thorough. I'd like to have PRBS, sort of an in-band PRBS where it goes through the frames, but also generates lots of random data and gives me a bit error rate because we can't really get a good bit error rate just by talking and seeing if it sounds good. The vocoder is too good at recovering from small errors, which is great, but not helpful for testing.
Okay. Would that be a valid issue to write on those repos to record it?
And that's a matter of philosophy, whether you think wish list items are issues or not.
I do. So if it would help to get visibility on this direction, then go ahead and file an issue.
I could do that.
Thank you.
I think that's all I had.
Thank you. That's a lot. Very appreciated. Thank you so much. And also thanks so much for all the extra hardware or software installed on remote labs and the work on supporting my Melody and integration of the Little Rock and San Diego remote labs. That's a lot of work. Very appreciated. And yes, the new hardware Chubb is a lot faster. So I know that in the future we're going to be doing some renovation of Remote Lab West from the Remote Lab South equipment. So thank you. That's
Yeah. To the extent that we're going to keep using the Marilla South equipment here, um, I have a medium term goal to get that computer out of my lab and into the remote lab because it's noisy.
yeah, it is. And you
You
can
could probably
definitely tell
you could
when
probably
you
hear
do
it if
build.
Zoom weren't so good at background or blanking the background noise.
Yeah. Yeah. But thank you so much for all of this. It's a huge amount of work and just makes it a joy to do builds.
It's a big difference.
Yeah. All right, I think that's it for the agenda. And again, floor is open for anything for the recorded session. Okay, so what I'll do is I'll just end the recorded session and we'll go into office hours if anybody has anything that they want to talk about. And I'll stay here as long as you need. Thank you so much to everyone for donating time to Open Research Stuff. It is deeply appreciated. We could not do this sort of ambitious work without you. And just thank you very much.